Alrighty, guys, we're going to do our final lesson for Unit 2, which is going to cover tonicity and osmoregulation. There's a happy little SpongeBob meme for y'all. So first, let's talk about tonicity. And if you remember this diagram at all from your freshman year biology class, that's basically what we're going to talk about. But first, we need to talk about a concept called water potential. So water potential, and let me go ahead and write it up there since I apparently forgot a title. So water potential is basically the potential of water to do work. It's free energy in water. What it basically means is that you're basically measuring how free water molecules are. Remember, water is polar, therefore it is attracted to other polar or charged molecules, charged atoms, charged ions, etc. And so if it is kind of locally, lightly hydrogen bound to another molecule, it's not free to move and do work. So when you add something to a glass of water, container of water, here we have a salt crystal. So we can just call it sodium chloride if we want, with positive and negative ions in it. This is when it first gets dropped into the water. As it stays in the water more, what you'll start to notice is more and more water is going to get kind of taken up or bound by these ions that are separating off. And so those water molecules that are attracted to those ions are not free to move around and do any work. And as more time passes, you start to see more and more water molecules getting bound up. And the consequence of this, and I'm going to circle stuff, but there's going to be more that I don't even see. So, the consequence of this is you start out with a certain number of water molecules in a container of water. You add solute, and as you add more solute, more of the water molecules start getting bound up to the solute, which is going to actually decrease your water potential. And water potential, by the way, is always represented by the symbol psi. That's a capital psi. Looks kind of like a pitchfork or a trident. And so when you add solution or add solute to a solution, that is going to decrease your water potential because it decreases the amount of free water. And that's the really big takeaway from this slide. The rest of it's just kind of explanation to try and help you understand the concept. But that relationship is really important for you to know because that's going to help you with any kind of conceptual free response questions dealing with water potential. So, how do we measure water potential? Well, it's measured in units of pressure. If you're having water potential calculations, they'll give you the unit. So you don't have to worry about what unit of pressure they're using because there's several. All right, so the standard is pure water. So plain water, nothing in it, nothing dissolved in it, in an open container has a water potential of 0. The reason why it's got to be an open container is because the container you stick this in can exert pressure potential, basically add pressure to the water. And so if you're in an open container, you don't really have an effect of pressure, meaning you can um, basically this water is free to expand up or contract down because there's no restrictions from the container. Whereas if this was sealed off, the water would only be able to expand so much, and at a certain point the walls of the container, if the water tried to expand beyond that, the walls of the container would be holding it in. So as soon as you add solute to any sort of container of water, any pure water, you start to decrease the water potential, which means it's going to become negative. So solute potentials are always negative. Okay? Pressure potential can be positive. And then if you need to calculate the total water potential of any given solution, you're going to add together the pressure potential of its container and the solute potential. If this is an open container, You don't got to worry about the pressure potential because it will be zero. So let's define tonicity. Tonicity is basically the ability of a solution to change the water concentration of a cell, and it doesn't do this actively. Remember, this is all osmosis, and osmosis is a form of diffusion, which means that it's going to happen passively, which means this happens without any energy exerted by the cell. So if you change the concentration or the strength of a solution surrounding a cell, you can affect how water enters or leaves the cell because it will diffuse down water's concentration gradient. And this is really different from how we tend to standardly think about concentrations, because normally we're measuring the concentration of solute, but we need to think for osmosis in terms of concentration of water. So if you think of it, you can think of in a specific container, you have a certain number of molecules that will fit in there. So if you have more, let's say you have 100 water molecules, that is a tiny, tiny amount, and you have like 50 solute. You have 150 molecules total. A third of that is solute. That's highly concentrated. But if we have another container that's also 150 molecules, but we only have 10 of our solute and we have 140 of our water, same volume, different concentration. The higher solute concentration basically means there's a lower water concentration. This lower solute concentration means there's a higher water concentration. So when I talk about things, that's what I'm going to talk about. So you have three types of tonic solutions: hypotonic, hypertonic, and isotonic. Hypo means less than, little. So hypotonic solutions will tend to have less solute. So this guy comparatively is hypotonic. On the other hand, hyper means extra or a lot. And so hypertonic solutions are going to have extra solute, so the higher solute concentration. Water is always going to flow from a hypotonic solution to a hypertonic solution. This also means that water flows from high water potential to low water potential. So remember, more solute I add, the lower the water potential. So this is going to have the lowest water potential. This is going to have the highest water potential. And water is going to flow from hypotonic solutions to hypertonic solutions. Water also flows from a higher water potential to a lower water potential. So that just shows the direction that water is going to flow. And isotonic, iso means equal. So an isotonic solution has an equal concentration of solutes and water as the cell insides. So let's look at what happens to different cells when you place them in these different solutions. So we have here a higher solute concentration outside the cell, a lower concentration solution inside the cell. So remember, if we have high solute, that means we have low water. If we have, let me pick a different color here. If we have low solute, that means we have high water. Okay? Water is always going to move from either a hypotonic solution to a hypertonic solution, or it's going to move from a high water potential to a low water potential, or it's going to move from where there's more water to where there's less water. So what you would expect is you would expect water to start exiting these cells. Water is going to flow towards where there's less water because basically the concentrations are equalizing. All systems in nature want to reach equilibrium. They don't even need to put in energy to do that. So this is a hypertonic solution. And as you can see from this diagram down here, our cell ends up shriveling. We also can call that crenellation. And that's not good for your cells. If you ever end up with your cells sitting in a hypertonic solution, meaning the fluid outside of your cells is hypertonic, that's not good because your cells are going to start losing water and they're going to die if you don't fix that. So, what if we have instead a low solute concentration outside and a high solute concentration inside the cell? Remember, if we have a low solute concentration, we can think of that as having a high water concentration. If we have a high solute concentration, we can think of that as having a low water concentration. So we have a hypotonic solution on the outside, a comparatively hypertonic solution on the inside. Water always flows from hypo to hyper, which means water is going to enter the cell. All right, when that happens, if you look at this diagram down here, this guy right here, water keeps entering the cell. We're animals. We don't have cell walls around our cells, which means that basically these cells are going to keep getting water in them until they lyse or pop. Ew, sorry, I wish that came up on top of the ink. So that's just your happy little cartoon to show you lysis. So then we have our third type of concentration, which is isotonic. Equal concentrations of solution inside and outside of the cell. Well, just because they're equal concentration doesn't mean that water stops moving. Instead, it moves in both directions, but it just does so at equal amounts. So the amount of water entering the cell will be equal to the amount of water leaving the cell. So you'll have equilibrium, and that is actually the ideal condition for animal cells. So you expend energy to maintain homeostasis and keep the solution outside of your cells isotonic to your intracellular fluid or your cytoplasm concentration, cytosol, etc. Now let's look at this in plants. We have a plant sitting in a hypertonic solution. So we got hyper on the outside, means we've got relatively hypo on the inside. Water flows from hypo to hyper. It's going to leave the cell, and that causes something called plasmolysis. The cell, when it gets to this point, this plant is basically dead. This is like a dried up husk of a plant. This is not good. When you have an isotonic solution surrounding a plant cell, you're going to have equal amounts of water entering and leaving the cell, and it's going to, be kind of mostly full of water. However, notice that there is gap between the cell membrane and the cell wall. That gap makes the plant kind of compressible, and we call that condition flaccid. When a plant has isotonic solutions outside of its cells, it is going to be wilted. That is when you have stopped remembering to water your plant, and it is basically like leaned over, looking like it's really, really sad. Yeah, that's when you know you need to water your plant. It's still savable at this point. So if you're like, okay, none of those seem good for the plant, what's the good condition for the plant? Well, tends to be hypotonic solutions. More water outside of the cell means that water's going to keep entering the cell, and it's going to keep entering the cell. But what prevents it from lysing is our happy little cell wall. So anything with a cell wall has extra protection against lysing because it's got that stiff barrier. So this type of cell, we say, is turgid. Turgid cells are completely firm, meaning you can put extra weight on them, they won't compress, and this is the healthiest condition for a plant cell. Remember, plants don't have bones. While they do have some materials that can help them stay upright, they're still not, able to counteract gravity on their own. They need something to help with that, and that's the turgidness of their cells. So this is their ideal condition. So we've got a number of calculations that go with this. This is another place where we have math. Luckily, it's fairly simple math. All of these formulas are on your formula chart. There's an entire section for water potential, so it shouldn't be hard to find. And we already kind of looked at this earlier, that the total water potential in a cell is going to equal the pressure potential, or in a solution, plus the solute potential. Remember, solute potential is generally negative. Pressure potential is generally positive. So the total water potential usually kind of depends on which one of those is bigger. If there's more pressure potential than solute potential, you'll have a positive water potential. And this is why it's also extremely important when you're doing water potential calculations to pay attention to the signs. So, what is the solute potential? It's also sometimes called the osmotic potential, and it is basically kind of a reflection of your solute concentration. The more stuff you have dissolved into water, then the lower the solute the lower the solute potential. So, as you add solute, you're going to decrease your water potential, and water will have a greater drive to move into that solution. There is a way to calculate it. I haven't seen this show up on the AP test for a little while, but I want to go over it just in case. The big takeaways are temperature is part of this formula, and it's measured in Kelvin. This formula is on your formula chart that you add 273 degrees to whatever Celsius you're given. This value R is a constant. It is also supplied on your formula chart. C is the concentration measured in moles, in molarity or moles per liter. Kind of the inverse of this part of the constant. And you'll be given that, or you'll have to solve for that. The one I really want to talk about is the ionization constant. The ionization constant depends on whether a molecule dissociates or separates into multiple ions. So let's say we have sodium chloride. When you stick sodium chloride in water, it's going to separate into sodiums and chlorines. And each of those is going to be capable of, drawing its own shell of water that will then not be available to do work. So it's going to decrease the solute potential, but it's going to decrease it twice as much as something that does not dissociate. So if we're looking for something else that doesn't dissociate, let's look at this old friend, C6H12O6, glucose. When you stick it in water, nothing changes. It's still C6H12O6. And so it has an ionization constant of 1. It's going to have half the impact on your water potential that something like sodium chloride does. And if you had, let's say, CaCl2, that is going to dissociate into a calcium ion and 2 chlorines. That would have an ionization constant of 3. Also, pay attention to the fact that you've got a negative sign there. So whatever answer you get here, you're going to basically make it a negative value, because remember, solute potential, always negative. So now we have a couple of problems that we're going to work through, and you've got space to work through these on your notes. However, since this is digital year, what you can always do is you can write these problems out on a piece of paper, take a picture of it, and then insert that picture into your notes in the appropriate spot. So that is just a suggestion for you.